All right, a little bit more circle fun and some more examples for you. All right, so we have a circle. We have UV as the diameter of that circle. We know that TU is equal to 6. We know that line TV, which of course looks like TU because my penmanship sucks, is 8. They want to know what the radius of this circle is, okay? So let's fill in some things. So TV is, again, 8. TU is 6. Now, we know that this is the diameter of the circle. Now, you might be like, well, how might I be able to figure out the radius? It doesn't seem like there's a lot of information. Well, some of you might say, like, well, this triangle looks like it's a right triangle, and we could use the Pythagorean theorem to figure out what this length is. And if we know what that length is, we can then find the radius, because, again, it would be half of that diameter. But we need to be able to prove that this triangle is indeed a right triangle. Well, luckily, we can. UV, because it's a diameter, this arc UV, which is, again, that whole length here, the measure of it angle-wise, aka tied back to the central angle, like I had said previously, diameters would split the circle in half. Therefore, angle-wise, if a circle is 360, half of 360 would be 180. So this arc measurement would be 180 degrees. Now, why that would make that 90 is because if you think about it, this corner of the angle is on the circle. It's reaching out to U and V. Angle T would be what is known as an inscribed angle, like we talked about last time. And inscribed angles are half the central angle of a arc, right? So because the measure of that central angle for UV is 180, or the measure of that arc, half of 180 would be 90. So this inscribed angle would be 90. And because that's then a right triangle, we can then use the Pythagorean theorem. So I'm going to go ahead and start the Pythagorean theorem out. 6 squared plus 8 squared equals this whole length x squared. 6 squared plus 8 squared would be 100. And then we would square root both sides, boink, 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 and x would equal 10. Now, that's not our final answer. That would just be the diameter of the circle, right? Because it would be the whole length. So half of that would be the radius. So the radius of this circle is equal to 5 units, right? So that's something you could use what we've been learning with last time for a problem that includes like length. Let's take a look at this problem. So LM, line LM, is a chord. Now, what a chord is, the definition of a chord, is a line in a circle. That's it, where its two endpoints are somewhere on the circle. So I could draw any arbitrary circle, right? As long as I'm drawing a line that's connecting one end of the circle to the other, that would be what is known as a chord. Not to be confused with a guitar chord or a music chord. In geometry, it's a little less exciting. It's just, again, a line that connects a circle together. Now, diameters can be chords, but they're a special kind of chord, right? So just because it's going from one end of the circle to the other doesn't necessarily mean it's a diameter. It just means it's a chord. So LM is a chord in circle P. Again, that symbol means that the center of the circle is dot P. The radius of P is 6 units, so the distance from P to the outer edge of anywhere on that circle is 6. And then the measure of the arc LM is 150 degrees, so I'm gonna put that there. It says find the length of the chord, or LM. Now, in order to find this length, I'm going to have to think, again, triangles, because usually when we're finding length in geometry, we want to think triangles, because that's exclusively pretty much what we've been doing this year. So in order to make this situation a triangle, I'm going to draw in 2 lines. I'm going to draw a line in here, and I'm going to draw a line in here. Now you can see that I have a triangle LPM. Now, what's nice about this is I know what this length and this length is, because this length and this length would be a radius, because it's the distance from here to the edge of the circle, or the center to the edge of the circle. The radius is 6, so both this length and this length is 6. So this would mean that this is an isosceles triangle. Now, I also know a little bit about an angle in this triangle, and the reason being is if you take a look at this, 150 degrees, this technically right here would be 150 degrees as well, because this relates back to the central angle for that arc. And this is the central angle for that arc because it's on the corner or the center of the circle, and it's reaching out towards L and M. Now, can we solve something like this? You bet. There's a couple ways to do this. I could use law of cosines to do this because I have two sides and I'm trying to find that third side. Or I could just, split this triangle in two and then solve it that way. I think for today, I'm going to do it that way. So I'm going to take this triangle, I'm going to draw it a little different, just kind of drawing out its end, 6 and 6, and I'm going to split this straight down the middle. So that would be a right triangle now. Because of the way I split it, this length would be 6, and this angle would have gotten chopped in half. 150 divided by 2 is, anyone? 75 degrees. And what I'm interested in is finding this length here. And if I know that length, I can double it, and then I would get the length of the entire thing. So this is setting up a nice little SOHCAHTOA problem for me. Where this is the angle, this would be the opposite side, and then this would be the hypotenuse. Anybody want to guess what trig ratio that would be? Opposite hypotenuse? Well, it's sine. So here we go. We got sine of 75 equals opposite over hypotenuse, and then we're just going to cross multiply. So 6 times the sine of 75 equals 1 times x, or in this case, just x. So I'm going to go to my handy calculator here, 6 times sine of 75, and I'm getting 5.79. So I'm going to just round it to 5.8 equals x. So this length here is 5.8. That would be 5.8. So if I double it, I would then know what my entire length of the chord would be. So 5.8 doubled is 11.6. So this length is 11.6 units long. So there's an example using chords and a little bit of what we know from previous units tied into what we just learned last time. Now, once in a while, what you'll get is two intersecting chords. These are both chords because, again, they're connecting one side of the circle to the other. Now, they give you some lengths, and they want you to find out this last length, right? But before we do that, I want to just humor me for a second, and I want to see if there's any relationships here between these two chords or these two lines. Now, if I imagine this as a triangle, and this one is a triangle. And the reason I'm doing this is because I know a little bit about proving relationships with triangles, because again, that's what we've done exclusively this year is with proofs is triangles, right? Now, a couple things I know is I know that this angle and this angle would be the same because of, vertical angles. But you might be wondering, well, what else do I know? I don't know really anything about like one being parallel to another or one bisecting another. I don't know any of that information. Well, what you do know is take a look at angle B and take a look at angle C. You'll notice that angle B and angle C are both inscribed angles to DA, or arc DA, right? They're both outstretched towards DA, which would mean that these two angles would have to be the same. Same is true for angle D and angle A, right? They're both outstretched towards B and C, right? So if you look at that angle A, its lines are going out to B and C. So these also would be equal to each other, right? So with that being said, these two triangles are similar. So if I know the lengths, I'm looking for a missing length here, proportions would be the right way of solving that. So let's fill in some information. So DE is equal to 8. AB, which is that whole length, is 10. Now, EB is 6. So what I'm going to do is, instead of writing 10 here, I'm going to break this down. I want to find out this segment and this segment separate. So EB, let's say here, is 6. Well, if this whole length is 10, what would that length be? So it would be, what, 10 minus 6, right? So that would be 4. And then last but not least, they want us to figure out what EC is. So we'll do that, right? So this would just be similar to each other, right? Now, we can't prove that they're equal. The reason being is obviously these sides would have to be all the same if they were equal, which they aren't. But now we can at least figure out like which side matches with which. And the way we can do that is taking a look at which angle matches which angle, right? So clearly this 8 either matches 4 or X. Now, you'll notice I put a triple band and a single band. there's a triple manasegment. So it's this 8 and 4 that are matching each other. So 8, 4 equals, and then the 6 and x are matching each other. So 6 over x. So because these are similar, I can write a proportions problem to solve them. So 8 times 6, we're going to cross multiply here. 4 times 6 is, 8 times x is 8x, and 4 times 6 is 24. Divide by 8, and then x equals, what is that? 3. There we go. So the answer would be 3. That length is C, or 3. Now, if you look in a textbook, they would have a formula usually for two intersecting chords. So if I have two random chords, right, and we'll say this length is A, this length is B, this length is C, this length is D, the relationship based on what we know here would be that A over B is equal to C over D, and you can use that kind of setup anytime you're given two chords that are intersecting each other. That setup would always help you solve for either A, B, C, or D. So you might see that in a textbook, or even if you did look through our textbook, they have the same kind of relationship on there. Okay, let's do one last example, and then I'll teach you one last new thing, and then we are done for the day. So I got this shape inscribed into a circle, and they want us to solve for x. The only thing they give us is that angle C here is 100 degrees, okay? Now you might be like, well, this is impossible. There's not nearly enough information. I do know that, like, for instance, this, and this angle add up to 360, right? Because it's a four-sided shape. But other than that, they don't seem to be giving me enough information. So let's go back to what we did last time. So 100 degrees is a inscribed angle for which arc? Where are the arms for this angle pointing towards? B and D, right? So this arc here, so from here all the way around to this point D, that's what it's pointing to. So the measure of that arc would be double what this number is, because this is just the inscribed angle, not the central angle, right? So again, if I want to find the central angle, aka the measure of that arc, I would double that number. So 100 times 2 is 200. So this whole from B through A to D, in fact, you would probably label it like this: the measure of that arc is equal to 200 degrees. Now, I could also find out the measure of this arc from B to D, right? In fact, they would probably call this measure BCD. And the way I would do that is I would know that a full circle, central angle-wise, has to add up to 360, right? So if I know that this part of it is 200, the rest of it has to be 360. And if I did 360 minus 200, that would give me what my arc length here is, and that would be 160. Because that would make the whole entire thing add up to 360. Now you might be like, well, why is that important? Well, if you take a look at x is also an inscribed angle, again, because its corner is on the circle. And you notice that its arms are pointing out towards B and D, right? And those are the same two endpoints for that arc. So if I know what that arc measurement is, which is 160, to figure out what x is, because it's the inscribed angle, the relationship is that it would be half of that. Well, half of 160 is, anyone? 80, right? So x is actually equal to 80 degrees. So a couple cool tricks that you can definitely do with some of the new circle relationships that we've been learning. All right, last but certainly not least, something new for you: tangents and secants. So not the idea of a tangent ratio, which is opposite over adjacent, but when I'm talking about tangents and circles, I do want to just mention what those are, because these will come up in either homework problems or in possibly SAT test questions, and I just want you to know what they mean. So if you draw a dot on a circle and then draw a line so it perfectly goes through that dot and only that dot on that circle, this is what is known as a tangent. It only goes through that dot, and it's a line intersecting the circle only one time, okay? If it's intersecting more than just that dot, then it's not a tangent line anymore. Now, another cool, I guess, relationship about tangent lines is if you look at the center of a circle and you take a look at its radius, right? So this would be its radius, and this would be the tangent line. The angles that are formed from that radius going into that tangent line are going to be 90-degree angles. So another way of thinking about it is tangent lines are perpendicular to radiuses, or radii would be the proper plural term. You might want to jot that down. So again, tangent lines are always perpendicular to circles' radiuses. And again, a tangent line is a line that just intersects the circle uno times. Another thing that you'll see is what is known as a secant line. A secant line, similar to a chord, is a line that goes through the circle 2 times. And that is the definition of a secant line. So similar to a chord, again, the only difference is instead of it being a line segment, it's a actual line. So it's a line going through the circle twice. The cool relationship for secants is that if you draw a center of a circle and then you have your radiuses here, this would be a radius, and then that would be a radius. Similar to the chord, this would always set up an isosceles triangle, or an isosceles triangle. And then what you can do from here is you can draw a third radius usually. This would create, like your right triangle, and people can use that for different other relationships as well. So there's just a quick run through of some other things that might show up in the future. Just wanted to let you know that these are things, okay? So hopefully these examples kind of give you a little bit more illustration on kind of tying some of the previous things we've done in this class along with some of the newer things that we did last time. And hopefully these inscribed central angle and arc measurements are starting to make a tiny bit more sense. Today's assignment, as well as today's attendance tasks, are going to be building off of what we've already been talking about. So hopefully that is helpful, and you kind of getting a better understanding of these, because I know we're just trying to cram this in here at the end of the year. Well, anyway, if you guys have any questions in this final week of class, holy crap, it's the final week of class, you can always drop by office hours. Office hours will be Monday through Thursday this week, final week of office hours, 1 to 2 p.m. Would love to see you guys drop in, say hello at least. If not, have a wonderful day, and I will talk to you later. Bye.